functions and inverses, understand the basics. Alright, when I talk about functions and its inverses, the first thing I need to know is what is a function. Now, various graphs are not all functions. We tend to think in our head a function is something that I draw a graph of. Not all graphs are functions. So that's the first important thing. The things that we do in high school, that you do in grade 11 and 12, the straight line, the parabola, the cubic function, the hyperbolic function, the exponential function, the log function, what else is there? The trigonometric functions. These functions that you do in high school are all functions. Alright, so how do I know if something is a function? I do the vertical line test, right? This tests if something is a function, right? That's what this vertical line test does. So how the vertical line test works is if I take a vertical line, for instance a ruler, and I make it a vertical line, this is horizontal, so vertical line, and I move over the function only cuts this vertical line once at all times. So if I look at the purple graph, can you see there's only one point where this graph touches the vertical line? There's the one point as I move across vertically with a vertical line as I move across. There's only one point where the graph touches the line, and that is then this is then a function, the purple line, which is, you can see, a cubic function. The pink line here, if I move across it with a vertical line, it only touches the line once at every point, and this is then a function, which is a straight line graph, and you know that's a function anyways. But quickly look at the green line, the circle. As I move this vertical line across, there it only touches at one place, but as I move in, can you see the graph touches this line there and there? And if I move along, it touches the line there and there. So this, as I move across, there's 2 points touching the line at some places, not everywhere, but at some places. And the green circle here is then not a function because it fails the vertical line test. Right, if it passes the vertical line test, it only touches the graph once, like the purple line here, then it is a function. Right, and this is quite important because there's so much more we can do with functions in maths than we can do with things that's not a function. And the important trademark of a function is, that's why I do the vertical line test. For every x value, if I go down, there's only one y value. So for 4 minus 6, there's only this one y value. 4 minus 2, where x is minus 2, there's only one y value, right? So for every x value, there's only one y value, where if I look at the green circle, if I make x minus 2, then y can be 4 and negative 4.5. So there's two y values, can you see, for this one x value, then it's not a function. So in words, if there's only one y value for every x value, then it's a function. If there's more than one y value for a specific x value, then it's not a function. All right. And then another thing that's also going to be useful now when working with inverses is doing the horizontal line test. This is to test the mapping of the function. A mapping is just a word I use to say that how many x values is there for every y value. Alright, so there might be for every x value, it might be a function. That means for every x value, there's only one y value. But for a specific y value, there might be more than one x value that's valid. And then I talk about a one-to-one function. One-to-one function means it is a function meaning there is only one y value for every x value. But if it's 1 to 1, it means there's one y value for every x value and also one x value for every y value, or it can be a more to 1 function. Now the fact that it's more to 1, or the fact that it's a function, tells me that every y value has just one, or every x value just has one y value. That's the trait of a function. So for every one x value, there is, or for every x value, there is only one y value. But for every y value, there can be more x values than one. So that's a more to one function. And to test this, I do the horizontal line test. So then I just turn the line and I make it a horizontal line, and I do the same test. So if you look at the purple graph now, I know the purple graph is a function, meaning for every x value, there's only one corresponding y value. But if I test it like this, can you see where y is 2, this graph cuts the horizontal line at 3 places. So I've got 3 x values, 5, 2, and minus 5, minus 2, and 5. So I've got roughly, I've got 3 x values for this one y value 2. I only have one y value for minus 5 and for minus 2 and for 5. There's only one y value, but I've got, it's actually more closer to 7. Sorry, I read 5, it should be 7. But I've got more than one x value for a specific y value. So then I do the horizontal test, and if it cuts more than once, then it's a more to one function. If I look at the pink line, if I move down with the horizontal line, the pink line only touches the horizontal line once. Can you see? So the pink line constantly just has one value. That means that this pink line is a one-to-one function. It has one y value for every single x value, and for every single y value, it also only has one x value. All right, so if I go and see that. So vertical line test for testing whether it's a function or not, horizontal line test for testing whether it's a one-to-one function or a more to one function. And it's not really going to be necessary to test for a more to one function with the green circle, with the circle, because it's not a function. Right, it already failed the vertical line test, so this is not a function. It is a more to one relation, but it's not a function. Right, whenever something's not a function, I can call it a relation, because there is some sort of relationship between the two numbers, but not functional relationship. Okay, so that is vertical line test and horizontal line test with functions and inverses. Now, why the horizontal line test is useful for inverses is if I take this function and I get the inverse, what do? I swap the x and the y values. And if I swap the x and the y values, what's happening? My y values, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, is now becoming my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x values. So this axis is going to lie there, and this axis is going to lie there. So what's happening? I actually fold the graph on this line, the y is equal to x line, which is not drawn in here. But then all of my, where y is 10, x is now going to be 10. And where x is 10, y is now going to be 10. So if I get the inverse, I swap my x and y values. And then negative 10 is going to, on the x-axis, is going to become negative 10y. And negative 10y value is going to become negative 10x. So can you see it maps onto one another like this if I fold it there? So what will happen is I take this graph, I reflect it on this axis. So this bit goes there, this purple curve there goes reflected on this axis there, and this purple bit there goes reflected on this axis there. Can you see? So then I reflect it. But now if I reflect it like that, if I make my y x and my x y, can you see that if it was a one-to-one function like this, which means also for every y value there's exactly one x value. So if I swap them, then still for every x value I will have one y value. This sounds quite complicated. It's not. If I swap my y and my x, if it was a one-to-one function, meaning for every y there's one x and for every x there's one y, if I swap my x and my y, then I will still have a function because it's still one-to-one. Right? But if I swap a more-to-one function like the purple one, now my x values, which for my x values in this function, I only have one y value, but for my y values, I have at some places 3 x values. Now, if I swap my x and my y, then for some of the x values, I will have 3 y values, which means it will fail the vertical line test. So if I have a more-to-one function and I get the inverse of that, it's not a function anymore. If I have a one-to-one function and I find the inverse of that function, it will still be a function and it will still be a one-to-one function actually. So mapping helps me with the inverses, and then what will happen, you will see if we do some examples, what will happen if I find the inverse of a more-to-one function, I swap it, then I will have to put restrictions. So say for instance I take this graph, which is a function but it's not a one-to-one function, and I take the inverse of this, I will have to restrict the x values. So then I find a bit of this graph which is a one-to-one function. So for instance, if I start here and I take only this bit up until there, if I move with the horizontal line test like that, if I only look at this bit of the purple graph, I take that away, right? So if I only look at this bit and I do the horizontal line test, then it's a one-to-one function, that bit. So then I'm going to say, before I start taking the inverse, I'm going to say my x values, well, this continues, but my x values say must be smaller than roughly -3, right? So then I say, okay, from negative infinity up until -3, my x values only lies there. Then I can take the inverse of that bit of the graph and it will still be a function. Or I can take this bit from there to there, which just goes down like that. And if you stop the graph there, if I have this bit, then I have 2 y values, can you see? So then I stop the graph there, and if I do the horizontal line test there, there's only 1 value. So then I can say from where x is -3 up until where x is, let's just say 3, roughly. Okay, so from where x is 3 up until where x is from where x is -3 up until where x is 3, my graph is also a one-to-one function. So then you can use this bit, take the inverse of that, and then obviously your y, if you invert, the y will be restricted in the inverse function because you swap them. So if I restrict the x's here, my y's will be restricted in the inverse function, and then I can also restrict it there for that bit of the graph. So sometimes they will say like a graph like this can be restricted in 3 different ways so that the inverse still produces a function. Sometimes they will say choose show 3 different options where this inverse is still a function. Sometimes they will say find the inverse of the function so that the inverse is still a function, and then you just take one bit. Sometimes that they will say limit x or restrict the domain to make the inverse a function, and they will say the domain must be bigger than 0. So then you will look for a bit where everything is positive x values, and then I'm going to use that. But as long as you understand that concept, that if it's a more to one function and I take the inverse, it's not going to be a function anymore. So, but if I take parts of the graph, which is a one-to-one function, and I inverse that, then I will have a function. So if they say restrict the domain, then the domain is the x values most. Then I'm going to just take part of the graph for certain x values. So I just state x must lie between -3 and 3, or x must be bigger than 3 for this specific function, and then you take the inverse, and then obviously y for that new inverse function must be bigger than 3. Alright, so that is basically what you must know about functions, mapping, and inverses. Just a kind reminder that the domain is all of the possible x values, and the range is all of the possible y values that you work with. If they do that, if they do ask domain and range, then sometimes they ask for what values of x does this graph increase or decrease. Good to know that if the graph moves up, like here, if I take the purple graph, if the graph moves up, then it is an increasing function, and the moment it turns down, then it's decreasing, and then from that point it's again increasing. Alright, so if they want to know for what values of x does the graph increase, for instance, then I go and see, okay, the graph increases here, and then I must go and state the x values where this happens. So I'm going to find the x values. Let's say it's at -3 where it turns, my turning point is at -3. So from where x is -infinite, because it goes on here, so from -infinity, if I look at the x-axis, this graph increases from -infinity up until where x is -3. If I look at the x values, this graph is increasing, then it's decreasing, and again from this point, that is where x is, let's say, it lies roughly between 2 and 3, so let's say between 2 and 2.5, right? So from where x is 2.5 onwards, so then again from 2.5 up until infinity, the graph increases. And if they want to know where the graph decrease, it's from there up until this purple graph is decreasing there, and there it's going to increase again. So the x values for where the graph decreases is from there to there, and then I just look at the x values in that spectrum, and that is from -3 up until 2.5, the graph. So then I will say x lies between -3 and 2.5. Right, and if you're unsure about how to write sets of numbers, there's a video in the basic sets, in the basic knowledge chapter, that does look at the interval notation and set builder notation. You can either use interval notation or set builder notation to write a set down, or domain and range down. So if you're unsure about how that works, you can just go and look at that video again. Alright, and then the average gradient, last thing I'm quickly going to discuss here. The average gradient of a graph just means the gradient, they just use average gradient when the graph is curvy, because you know the gradient has to do with the steepness of the graph, the slope of the graph, But if it has a curve, then its slope is constantly changing actually. But I still use this formula which you use for gradient, and I just call it an average gradient. So you're still going to use the same formula. Don't freak out if they talk about average gradient. It's very easy. You use the same formula. Say they want the average gradient between this point and this point, then you just use these 2 points and you substitute into that formula and you find the average gradient. Why they talk about average gradient instead of gradient? The gradient between these 2 points, between that point there and that point there, will be the gradient of this line from there to there straight, right? But the curve actually makes it that this is not a gradient. So can you see that at this point here, the gradient to the line that touches, the gradient is 0, and then the gradient becomes bigger, 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 bigger as I move there on the line. So the gradient actually, the gradient of the line that touches, the tangent, changes. But then actually it's proved mathematically that if I take all of these gradients, it's going to take me forever. But if I take all of these gradients and I add them up and I divide them by the amount of gradients that I took, it's actually going to give me the same gradient as the line straight from that point to that point. Same here on the circle. Say for instance I want the gradient from this point on the circle to this point of the circle. Now this line going through there has a certain gradient of roughly 1. If I look at the slope, it looks like almost 45 degrees. Right, so this line has a gradient of 1. But if I take a gradient of -1, -1/2, -3/4, up until a gradient of 0, gradient of 1/2, gradient of 3/4. I type all of these gradients as I go along the circle. Gradient that doesn't exist even there. Gradient of -15, gradient of negative, and I add all of these gradients around the curve together. And then just divide by the amount of gradients that I added. Then I will roughly get this. Right, so that's just what the average gradient is about, but don't break your head about it. You literally, if they want the average gradient, that just means it's on a curve, but they just want the gradient between these 2 points if I go and draw a straight line there. But because it's a curve, they will talk about average gradient. If it's a straight line like the pink line, they will just say determine the gradient of the line. All right, so that is average gradient. Yes, so this is all you need to know about, in a nutshell, about functions and inverses. Knowledge that we are going to apply with your grade 10 and 11 knowledge of functions, using the formula, sketching the graphs, determining the domain and range, finding the formula from a graph, things like that. General typical questions with find the inverse, etc.